Okay, recording. Okay, so we're going to set up a 50 microliter reaction for our PCR because it's all based on the machine. So the higher volume in the tube, the longer it takes to come up and down to temperature. And so if you have a really fancy machine, you can just do it in 25. If you have an old crappy machine, you have to do it in 100. We have a middle of the road machine. So we're going to choose the 50 microliter reaction volume for PCR. And so that is, it'll take a little longer to come up to temperature than a 25 microliter reaction, but it's also less susceptible to pipetting error. So if you put 1.2 microliters into 50 instead of 1.0, it makes less of a difference as putting it into 25. So pipetting error makes more of a difference in a small volume than a bigger volume. But it's not so big that we have to worry about, oh my gosh, we have to let the machine run, you know, for minutes on end to make sure it comes up to temperature. So we're going to do a little bit of review about our volumes and so forth. So if we want 50 microliters, so this really means up to 50. So our total volume is always going to be 50 microliters. And we are told that our master mix, which I think we talked a little bit about last time, and if we didn't, the master mix has the polymerase in it. It has all the DNTPs. It has all the buffers, so the salts, the magnesium, everything it needs to work, right? Except for your primers and your template, because those are specific to your reaction, right? We're making our own primers, right? We're not using control primers or something that came with the kit. So we have everything all together. Some kits, all of that comes separately. And so you're pipetting in 2 microliters of this, 2 of that, 1 of this, 3 of that, 4 of this. The more times you pipette, the more error comes through. So, yeah, I went away. So this way, the master mix, all of it's in there. You pipette one thing, they put it at a 2x concentration. And so if they didn't tell you the volume here, how would we figure that out? M1V1 equals M2V2, right? So we always love that guy. Or C1V1 equals C2V2. Oh shit, I can't even read my own writing. Okay, so we know, and it doesn't really matter which one you make 1 and which one you make 2. You just have to think about what you have and what you want, right? So we know what we want, right? We want the final concentration to be 1x. So M or C, so M mass, C concentration, in a volume of 50 microliters. So we know that's what we want. That's the given. What do we have? We have 2x. What don't we know? We don't know V1. Can't write that small. Okay. So our equation is just 2x times V1 equals 1x times 50 microliters. And so then we do the math, right? Remember, if we divide both sides by the same thing, right? That's fair game for an equivalent setup. I don't know what you call it. And then we make the 2x's cancel, right? 2x divided by 2x is 1. 1 times V1 is just V1. 2x, the x's cancel, right? And then you have to do 50 times 1 is 50. 50 divided by 2 is 25. So V1 equals 25. We carried our units. Microliters are left over. And so we have 25 microliters. So if it didn't tell you what final volume, it just told you, right, what it is, our start, and what you want at the end, you can always figure it out. So if your master mix is 10x, what do? This equation with a 10 instead of a 2. What if it's 50x? What if it's 3x, 5x, 6x? Doesn't matter. As long as you know what x you want at the end, which is almost always 1x. unless you're taking a really concentrated solution and making, like if you're going, you bought 100x and you need to make a 10x to work with the next thing, right? Otherwise, your end concentration is almost always a 1x. But it doesn't matter whatever the final concentration is, right? And you know your final volume, you can always figure it out, right? So you always have 3 of these items in order to use this equation. Okay, and then we made our primers, right? That was our calculations we did, and we set them at 10 micromolar, right? And we're gonna say we want them at the final concentration of 1 micromolar, right? We have options, and that's just because depending on your reaction and blah, 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 you can always, you know, you can use less or more. We're gonna say we want them at 1. And so if we have a 10 micromolar solution and we want to end up with 1 micromolar and we know we're in 50, we can do our M1V1 equals M2V2. Yes? Yes? Is anybody there? Hello? Yes. Okay, you can always thumbs up me too. Just, you know, talking to black boxes is hard, as it turns out. Okay, now I can see a few more of you if you give me the thumbs up. Oh, yay, I got thumbs up. It's kind of like a sticker. You know, I love stickers. Okay. And you know, I love you guys too. So what could be better? All right. So somebody do that math and tell me what the answer is. So I don't have to do it on my phone. Or we could just, yeah, let's do it. Let's pretend, because pretending is good. Because then the more practice, make those neural connections, right? Make it easy to do these stupid calculations over and over and over. Okay, so we want 1 times 50 is 50. 50 divided by 10, is that true? Okay, 5. So we're gonna say that's 5. Right? Did I do the math right? Did everybody get 5?
Yes.
Yay, I got a yes. Okay, so our DNA template, holy crap. Remember when we made genomic DNA and we said we isolated 15 micrograms? Isn't that what we said? I'll scribble this out so you don't think I'm writing down here. So I think when we pretended to make genomic DNA with that kit, we said we got 15 micrograms. Remember, we could expect 10 to 20, and we said we're going to get somewhere in the middle. We're not going to totally suck at it, but we're not going to be awesome. And then I don't remember what we said we were going to put it in for that little homework thing, but let's pretend, unless somebody remembers. We'll say we put it in, 200 microliters of TE. Right, we resuspended it, and that gives us what concentration? How many micrograms per microliter? Shout it out, people. You're all hiding from me.
0.075 micrograms per microliter.
Betcha. You betcha, my sister. Okay. I'm scribbling in this little corner. I have to scribble out all this shit. Right. Oh, I was going to use my notation. Okay, so 0.075 micrograms per microliter. And this guy says it like less than 250 nanograms. So let's pretend like we're going to add 200 nanograms just to be safe. Well, we have to do a little conversion, right? Because we're in micrograms and this is asking for nanograms, and we can't forget to do that or we totally screw this up, right? Because we'd be off by 1,000-fold, right? So micrograms to nanograms, right, is 1,000-fold. So we have to essentially multiply by 1,000, right? We're not allowed to move decimals, remember? So if we multiplied, so if we say 1,000 nanograms are in a microgram, right? And we have 0.075 micrograms per microliter, then we get, sorry, it's kind of scribbly, our micrograms to cancel, and we do this math, and we get nanograms per microliter, and what we end up with is that true? 75 nanograms per microliter. Right? Or the old, so that's our Common Core method to make sure we understand and we carry our units so that we can't forget which way do we put the stupid ass decimal. Or in our old fashioned way, like we just move the decimal 3 places. Right? So that's how we get, so now that's our concentration. I guess I should have written it over there. Right. And so now we want 200 nanograms of that. And so we just take, you know, well, what do we need? 200 nanograms. What do we have per microliter? We have 75. So if we divide that by 75, we need to add, I'll put it back in my red, 2.666666667. So I'm going to say 2.7 of that guy. You believe me? That makes sense, right? Because if we multiplied 75 by 2.7, we'd get about 200. So you can do the math forward and backward, check your work, right? I think that's is that the additive rule or something like that? I don't remember. That was like 3rd grade. Right? Working forwards and backwards across the, whatever. Okay, I got Common Core to death. Kids are in grade school. But it made me remember, right? So, and I'm old, so that's good. Okay, so what's the next thing? Now we need to go up to 50. If we added 50 by accident, we weren't paying attention, we'd blow the shit out of our reaction. We'd have way too much, right? We'd have over 80 microliters in a reaction that's supposed to be 50. So we have to remember this, up to 50. So what do? We have 25 of our 2X mixture, plus 5 is 30, plus 5 of the other primer is 30, I almost said 40, 35, plus 2.7 equals 37.7 microliters already. So how much water do we add? We have to minus the 50, right? Or take 50 minus that 37, and we end up with 12.3 microliters of water. And then if we want to check our work, we re-add all this together and make sure it comes right up to 50, make sure we get 50 in a total, that's our total volume, right? Because we said up here, our total volume was supposed to be 50. And that's the only way all of these guys are going to be at the correct molarity, is if we're in that 50 microliters. Wow, that's scribbly. Does that make sense? Yes, thumbs up. Anyone?
Yes.
Bueller? Sorry. Oh, but oh yay, I got some thumbs up. Okay, can I reaction myself? I don't think so. Let's see. No, how rude. I can't give myself a thumbs up. That's pretty rude. You're supposed to have intrinsic motivation, guys. You're supposed to feel proud of yourself and give yourself treats, and that's better than extrinsic motivation by somebody else. I can't even Canvas thinks it's growth mindset. Oh no, this is Zoom. Sorry, Zoom. I'm gonna write an essay. Okay, sorry. Okay, so we're good, right? That all makes sense. We're happy little clams. Okay, I'm gonna try to squeeze us. Squeeze. So I'll keep that so we can kind of see it. But now we want to actually do. Now we have it all in our stupid little tube. Whoa, what is happening? Okay, in our little tube, and we're ready to actually do some PCR. And so let's talk about doing PCR. So we're going to have a machine, and we have to set our machine up so that it does PCR for our primers and our template, not somebody else's primers and somebody else's template. So there's guidelines, but it's really going to be pretty specific to what you need to do. So the first thing, if we remember our little videos about PCR, is that we have to denature the double-stranded DNA. So we put our template DNA, it's big pieces of genomic DNA. Even if we cut it up a little bit, you know, chromosomes are ginormous and we want all of those base pairs to come apart. And so we're going to heat it up and break those hydrogen bonds. In DNA replication, the bonds are broken by helicase, right? Remember, I got that wrong. Right? Bonds are unzip your DNA, break those hydrogen bonds, create that replication bubble. In this case, we're just blowing those chromosomes apart. So everything's single stranded in there. Okay. And they say, you know, a couple minutes to do that just to make sure. So if we have an older machine, we're going to do a 2-minute at 95 degrees Celsius. 100 degrees is boiling. So we're pretty much boiling the crap out of this stuff. So that makes sure everything's single stranded to start. Then we have to do our cycle step. So in the cycle, if we remember, right, we want to go heat to break the bonds. So we can call these our hydrogen bonds broken. And then we want to complementary base pair our primers to our template, which PCR refers to as annealing. And then, oh, I didn't make that firm. And then we want to actually make polymerase go and do polymerization, add nucleotides, right? So we're going to call them DNTPs, all the nucleotides, right? And they call that extension. Okay. So we want to have our primers anneal to our template, and we do that by lowering the temperature. And we want to lower the temperature, not so low that both of those template strands come together, but low enough so our little piece can find its template and sit down there. And we don't want to go any lower than that, because then the two templates will come back together and then you can't get PCR, right? You can't add nucleotides to something that is already double-stranded. It needs to stay open everywhere. It needs to stay single-stranded everywhere except where your primer sat down. So we want to optimize our annealing temperatures by making that annealing temperature start at 5 degrees below our melting temperature. So remember when we were designing primers and we kept talking about melting temperature, GC content, and our melting temperature in our list when we got our primers was called TM, melting temperature, temperature of melting, right? And we wanted those to be close together, right? So that was kind of why we wanted to try to make our GC content close together, because that contributes to melting temperature. But the computer gave us our melting temperatures and we picked primer pairs. If we got, I remember I got 7, 8 different pairs, and I picked ones that had the closest melting temperature. So we want to go 5 below the lowest, the lower of the two primers. And then we want to let that sit. It says 30 seconds to a minute because we have older machines. We're going to go a minute, and we're doing that 50 microliters. If we had 25 microliters, we'd just do 30 seconds because it could get that whole volume up to that temperature in about 10 seconds. And then it has 20 seconds to do the annealing. Whereas our bigger one is going to take us 20, 30 seconds just to get up to temperature. And then it holds, then it stays at that temperature for at least 30 to do its job. So the longer time is really just trying to get that temperature of that entire volume, not just the outside near, you know, the heat source as it sits in that heat block. And then we want to extend, we want to do the actual polymerization. And because we're using TAC, we're going to do 72 degrees. That's where he's happiest. So we're going to set that extension for 72 degrees. It tells us 1 minute for every kilobase or every 1,000 base pairs. Most of us have about 1,000 base pairs. So we do about a minute, or we might do a minute and a half just to be safe, right? And then, so that's where we're going to get our polymerase to go. If we were using one of those other polymerases I referred to before that does the proofreading, that guy actually works best at 68 degrees. So we'd want to match the extension temperature to whatever polymerase you're using. So don't just automatically punch in 72 because you might not be using a TAC polymerase. So you'd look at the instructions for whatever polymerase you're using and use that extension temperature. Okay, so for our first denaturation, we do 2 minutes. For the rest of them, we just do 1 minute. So our PCR cycle is first we do a long 2-minute denature, just make sure everything's apart. And then for our cycles, we have 1 minute at 95. We have 1 minute, I guess I didn't say that, but it's right there. 1 minute at our 5 degrees below lowest TM. And so a lot of times that's about 55 degrees. So we'll say 55 degrees, just, you know, for our little example right here. And then we do 1.5 minutes at 72 degrees Celsius. And we do this for 25 to 35 cycles. So we only do that 2-minute guy here once at the beginning, get everything super single stranded, can't possibly be stuck together after 2 minutes. And then we do break, they're already broken here, but we make sure they're still apart. We anneal those primers. Polymerase can now sit down and add complementary base pairing until it falls off. And then we go back to the next cycle, heat it up, break the bonds, cool it, primer sit, heat it a little bit to make polymerase happy. He grabs on complementary base pair, complementary base pair, complementary base pair, go back, heat, cool, warm, heat, cool, warm, heat, cool, 25 cycles. And then at the very end, we do a final extension of about 5 minutes. So like that's the addition at the beginning. We do a 5 minutes at 72 degrees. And that will allow polymerase to grab any 3' ends that have any length of template left that's not already filled in. So in case polymerase fell off early, like I had a moment and it fell off before it got through your 1,000 base pairs, then it'll fill those in until it falls off. So that just cleans up our ends. And then we're done. The PCR machines usually go to 4 degrees, which is refrigerated temperature, and they hold it there so that you can have time to put your samples in the refrigerator or get them out and do something with them, right? Or they can go overnight. You don't have to worry about them sitting at room temperature, blah, blah, blah. So that is what we're going to do to our PCR machine. Are we good? Are we thumbs up? Are we happy about PCR? Do we love PCR? We do love PCR. Yay! I knew you guys would say so. Okay, let me see now. I think for my next trick, pull a rabbit out of a hat. Okay. I think I quit sharing this, multitasking. I think I go back to here. Okay, yes. Okay, so that guy goes there. Oh, how do I get out? Oh, stop share. Should know about it. Ooh, here I am. And then we're gonna reshare. But I'm gonna share that guy. And I'm gonna find, oh, I had that on here. No, I am going to find my Word document. Oh, I probably closed it. Dang it. Let's see. Sorry. Here, we'll stop share and spy on my hard drive. All right, talk amongst yourselves. Here's a topic. It's almost Halloween. I'm going to go back to what I talked about in the little video, which refers back to our snap gene. That's what it is. Okay. And this is back to our annealing temperature. So I want to make sure we finish off with understanding that annealing temperature and then I think that's enough for today because it's almost 1:30. And then that's essentially where we left off on the Wednesday. So we'll be back in sync. Okay, hello, start sharing. Sorry, where's my Zoom? There's my Zoom. Okay. Here we go. Okay, so this is just my Word document of my primer report. So that was just what I showed in that tutorial. And also, so this is straight out of NCBI. So this guy was my reverse, the reverse primer that so this was my brain reverse, right? And then the top one was what the primer blast generated for me. And it gave me a bunch of primer pairs. And so when I looked through them originally, I had chosen pair 2 and pair 4 as my best guys. And remember, we were looking at self-complementarity, which is like, does it fold on itself? 3', did the 3' ends attach to each other? So will the primers stick to each other and themselves more so than your template? And we said under 10 is good, lower the better. And so we can't do anything about, the reverse guy. He's going to be the same in all of them because that's my brain. But we can look at the primer that the computer generated for us. And so I liked primer pair 4 because it had the closest melting temperature and the best over here. These guys' melting temperatures were off. This guy was 0 also, just like primer pair 4. But the melting temperatures were farther apart, like by, 0.03 or some stupid shit. But I had to pick something. So anyways, I picked primer pair 4. So this was the guy that I said is going to be my final primer pair. So those are the ones that I added to the snap gene in my tutorial. And it should give me about a 512 base pair piece. I think Snapgene said 513, just based on, counts a little different, whatever. And I look here, and so my lowest melting temperature is 60. And so if I subtract 5 for our rules of picking an annealing temperature, it would get me to that 55. So I didn't even lie to you guys in setting up that PCR. That would be where I would start with my primers, would be at that 55, because that's my lowest guy. So that doesn't mean it's going to work. Right? If you get nothing on a gel, that means no primer sat down except primer dimers, which again, next time I'll show you a picture of that. If you got nothing sitting down, no bands at all, either you totally screwed something up and you didn't add something to your tube. So you recheck your protocol and you make sure you made your checklist every time you added something that you marked a check mark so you don't forget which tube you're on. You would decrease that annealing temperature, make it easier for primers to sit, right? Remember we said the lower the temperature, the easier for anything to complementary base pair, which makes it easier for our templates to come back together. So you can't get super low or that screws you over, but you can drop down. And depending on what protocol and what machine you use, they say you can drop by 1, 2, 3. You might want to drop 250 and then say, okay, then I'll get lots of bands and I can increment back up. If you already get lots of bands, then you need to raise your temperature. Your temperature should go up to make it harder for primers to sit. If you have lots of bands, that means those primers sat in lots of places. And that brings me to our primer check. Why I had you do the primer check, because from the output from primer blast from when we did brain reverse and computer forward, I didn't get any mismatches. I had to put these two primers, I put into primer check. And here's primer pair 4, right? There's my things. And here's where they sit down. They should give you your locus, right? This is just scanning the entire genome, the human genome. The program doesn't know that's what you're PCRing, right? You're just adding these primers. And so, yeah, it better sit 100% complementary on your chromosome. So chromosome 22, that's where mine sits, right? The other strand, yes, right? This is that same, it's just cloned of that region. So that's still mine. This, yes, still the same thing. And then this is also another light chain that's very similar, blah, blah, blah. So it might sit there because it has one mismatch that's an isoform. So that we don't care about. Again, chromosome 22, yes. In this, it says it mismatches twice, but it's still giving us that same size. So that's nothing new here. Now we have a different chromosome and it says my primers might sit there. It mismatches 3 on this one and 5 on this one, but it's still within the realm of possibility. If my annealing temperature is too low, that my primers might sit on chromosome 9 and give me almost 1100 base pair piece. So I'd be on the lookout for that band on a gel. If I see that, I know I need to go up in temperature because it's sitting in the wrong place. If it sits here, it should also sit in mine. I should have my 500 and this guy. It shouldn't just be the 1100, but you know. And so we keep looking, that's the same one. Here's a different chromosome, right? This gives me a 4000 base pair piece. So we might see that. Here's that same 4000, might be 2500. And then here's the 2 that are around 1000. Those would be the closest to my 500 base pair piece. I want to make sure I can resolve those 2 pieces on my agarose gel. So I have to make sure I use the right percent agarose gel in order to run to see the difference between those 2. So it's important to know where else your primers might sit so that when you have your gel, you can make an educated decision about turning up your temperature and redoing it to remove some bands, or bringing it down because you got 0 bands, but then being on the lookout for what should show up. If your sequence doesn't show up and random sizes that aren't predicted, then we go back and make sure we didn't redesign our primers wrong, right? Or we thought we put in primer pair 4 and we actually put in primer pair 8. Right. So then we look for our errors on that. And we can troubleshoot by knowing what we're doing versus like, oh, I didn't get what I wanted. I don't know what to do now. Right. So that way you can think. And knowing what we need to resolve will help us figure out what type agarose gel to pour. So common percentages are 0.08%. and 1% and 1.2%. But 1.2% and 0.08% are a completely different resolution, and you might miss what you're looking for if you use the wrong one. So for our next week, I might try to make a little tutorial to get us a little head on the basics so that we can actually then just work with our sizes. I'll try to get my act together to make that tutorial ahead of time so you guys can watch it, and then we can actually get to work with our sizes so that we can pick a gel to pour, and then we can simulate what we would see on a gel. So you guys should all look at your melting temperatures of your primer pairs that you chose. Make sure you have your file of your misprimes somewhere handy. If you just took a screenshot, that's fine too. It does not have to be in a Word document, whatever's easy to find, but just make sure it's handy. And then we'll be ready to make gels. It's kind of like Jell-O. So, we could pretend and actually make some Jell-O. Oh, and then we actually get to eat it instead of just do something with it. But that will be our plan for next time. Are we good? Is that good? Do we have questions?